Good afternoon to everyone in Europe and good morning to our colleagues in the USA. So I'm Athanasios Kolios and I'm the president of the European Academy of Wind Energy. So it is a great pleasure today to welcome you all to this lecture from Dr. Haupt, who has been awarded the EAVE Scientific Award for 2022. So this is an award that the European Academy of Wind Energy gives every year to a leading researcher or scientist for seminal contributions in wind energy science. Since 2007, the award has been given to distinguished colleagues who we all recognize. So indicatively, recipients of the award are Professor Fred Glaber from Aalborg University in 2021, Professor Peter Tavner from Durham University in 2020, Professor Jim Manuel from University of Massachusetts in Amherst in 2019, and many other colleagues. So a few words for the recipient. So Dr. Haupt is a senior scientist at the National Center for Atmospheric Research and Deputy Director of its Research Applications Laboratory. She is also contributing and founding Director of the World Energy and Meteorology Council and Fellow of the American Meteorological Society, AMS, where she currently serves as Commissioner of the Commission on the Weather Climate Enterprise. So she earned her PhD in Atmospheric Science from University of Michigan, MSc in Mechanical Engineering from Worcester Polytechnic Institute, MSc in Engineering Management from Western New England College, Bachelor of Science in Meteorology from Penn State, and did the postdoctoral fellowship with the Advanced Study Program of NCAR. She has also been on the faculty of the Pennsylvania State University, University of Colorado, the US Air Force Academy, University of Nevada, and Utah State University, and worked for the New England Electric System and GCA Corporation. So Dr. Haupt is an expert in boundary layer metrology, large-scale atmospheric dynamics, applications of artificial intelligence in the environmental sciences, renewable energy, dynamical systems, numerical methods, and computational fluid dynamics. His specialty is in applying novel numerical techniques to problems in the environmental sciences in both basic and applied research. She enjoys teaching and mentoring graduate students, as well as developing and directing research programs and projects. So with no further delay, I would like to welcome Sue Ellen Haupt, and we are looking forward for your presentation.
Thank you so much for the kind introduction. I am incredibly honored to receive this award. It really is a huge honor, and I really thank the European Wind Energy Academy. Today I'm going to be talking about how meteorology enables renewable energy. But we're going to start back in history, where there wasn't much in the way of energy beyond fire, and of course that came from the sun. And early man discovered fire, and that's when they began to be able to socialize, and it really started spurring social development. Now, then, of course, eventually electrical generators were invented, and that made huge changes in how society developed. And we see that there was a huge evolution of energy usage over the last century and a half plus, where we went from that early use of wood only to adding fossil fuels like coal, oil, gas. We did develop hydro and other renewables. Nuclear came into play in the mid-1900s, and that allowed society to develop. However, the use of all those fossil fuels did add to pollution, global warming, by the emission of many pollutants. And the energy contributed to the world's problems in addition to the advance of society, the pollution that became prevalent, the global warming from the CO2, the social inequities because some countries developed energy resources early, others did not. Now, here's our maps of distributions of coal on the left, oil on the right over the world. We see that there certainly are countries and regions that have plenty of fossil resources, but there's also many regions that do not have those resources. And we find that the patterns of energy usage per person correlates with the availability of those fossil resources. And then when you look at social progress index on the y-axis versus energy use per capita, we see that the most developed countries here on the top right of the plot are those that developed energy early and have lots of access, while those with less social progress are ones that may not have as many energy resources. And that can lead to energy poverty. I grabbed this from a website for Habitat for Humanity, and I highlighted, according to the IEA World Energy Outlook in 2018, 1 billion people in the world, that's 13% of the total population, has no access to electricity. Most of that is in Africa and South Asia. Now, I also highlighted in particular Bangladesh, where some changes have been happening, where it used to be that only 20% of the population had access to electricity, but now it is up to 80%. So there's a lot of change. What is helping to drive that change? I claim renewable energy is making all the difference, not only in providing clean energy, but also becoming very economical. It's local, that provides energy security. And most form of renewable energy is available anywhere in the world. And it's variable. That's the issue. The atmosphere has become the fuel. That means we really need to understand and leverage what we know about the atmosphere to optimize our use of renewable energy. Now, I mentioned decreasing costs. Here is a plot from the newest REN 2022 that just came out recently, showing the changes in costs even between 2010 and 2021 of solar voltaics, concentrating solar, offshore wind, and onshore wind power. We see these huge decreases in costs that is making wind and solar some of the cheapest forms of energy in the world. Now, also from that same report, we see the deployment growing. You've all seen plots similar to this before. Wind capacity growing over huge amounts to being 845 gigawatts now. Solar, similarly, now at 942 gigawatts. And this is making a big difference. Let's return to Bangladesh that I mentioned before. We had an opportunity to do a project to help Bangladesh assess its wind energy resources in collaboration with NREL a few years back, where NREL's role was to site observational facilities throughout the country where they could measure the wind resource and profile it. It was very challenging to transport some of the instruments in Bangladesh. NCAR was able to do modeling of the resources and finding that when we looked at high resolution, there was a wind resource that was worth developing in Bangladesh, helping them to reach those higher percentages of access to energy. Now, the nice thing about meteorology is it transcends boundaries. We're able to get away from countries' sources and those that do not. And here is an animation of a global climate model where we see wind patterns. Also, that implies patterns in solar radiation that reaches the ground as well. And this we no longer have countries who don't have access to any form of energy because we're able to harvest the renewables. So this means that we have changing paradigms so that we can optimize the use of this renewable energy. We have this more equal distribution of energy resources, and meteorology has become the key to managing the energy system. We're able to observe the atmosphere. That helps optimize, model, and provide machine learning approaches to optimize our use of this renewable energy. Now, looking at scales in time and impact of meteorology on the energy systems, it's important from very short range, from the order of seconds, where things like lightning can cause flickering in the energy system, through minutes and hours, where passing clouds and thunderstorms can decrease solar power, disrupt energy usage. On the order of days, hurricanes can disrupt use of offshore wind as well as harvesting oil. Reduced hydropower on the order of months when there's times of drought. Over course of seasons, cold spells, heat waves, changes the demand. Over course of years, we have interannual variability where El Nino, Southern Oscillation can really cause changes in resources as well as impact maintenance. And then, of course, over longer terms, decades to centuries, we could see changes in the availability of renewable energy. So we're going to look at these scales and look at a few examples along these particular scales. But first, let's look at also the spatial variability. We have this global pattern that then feeds into the continental scales, where we have passing weather systems, where you see this beautiful cold front, warm front modeled going across the United States, that then impacts the flow patterns coming into wind farm scale, and of course, the fine scales feeds back up into the larger scales as well, which brings us to looking at the energy spectrum, where the energy at different scales in space and time, and we see that most of the energy in the wind is at the global scales. And there is a cascade, through the synoptic mesoscales into the wind plant scales, and finally to dissipation scales at the wind turbine scale. So how do we, understanding this cascade of energy and how to best leverage the information really can help us to optimize how we use wind. Now, I'm going to talk about a few different applications, beginning with forecasting for renewable energy. The need for that became apparent when some utilities, such as Xcel Energy in the United States, began to deploy large amounts of wind in a similar region over the course of, in around the early 2000s. And Xcel was one of the utilities in the United States that ramped up rather quickly, especially in Colorado. And they found they ended up having events something like this. Now, each color is power output from a single wind farm. But when you have a lot of wind farms in the same region, you find that even passing thunderstorms can make big changes over a short period of time. But then on this particular day in 2009, they had a cold front pass through, and that caused a very large ramp up, 800 megawatt increase in power output by wind over the course of 4 hours, and then a corresponding decrease. You need to understand and be able to forecast when this is going to happen so you can best use that available wind energy and be able to not use the fossil plants as you see these great ramps coming through, but you have to be prepared when there is a down ramp like this. So at that point, we need to think about how do we pull together a forecasting system for all these different scales. Well, on the shortest ranges, we have in situ observations. We need to leverage those optimally, and that often requires applying artificial intelligence techniques. Once we get past the latency for getting satellite data in, we can use some satellite-based methods. Then, if we are running very short-range numerical weather prediction models, we can start, having output that's available a course of an hour or so. And then, of course, the national centers are running high resolution, localized, specialized NWP, then regional NWP, ensembles of NWP, global models that are not put out quite as often. And then if we're looking at longer scale, seasonal climate modeling becomes important. But transcending all of that is machine learning methods that we can use to optimize any of these or blending them together. And that's the approach that NCAR has been taking over the last decade or so, where we blend the best of the scales that we need. We convert to the variable that is of interest to the end user, in this case, power, quantify the uncertainty of the forecast so they know when to trust the forecast the most to come out with a probabilistic power prediction. So because Excel had that high deployment early, they engaged NCAR to build a wind power forecasting system for them. NCAR leveraged wind farm data from the national centers, output from ND models. We ran specialized physical models, weather research forecasting model with real-time four-dimensional data assimilation, stood up an ensemble system, and then applied various artificial intelligence methods. At the center of this is the dynamic integrated forecast system, which I'd like to mention in a little bit more detail. Now, this is an artificial intelligence system built by NCAR, a couple decades ago, originally for the Weather Channel, where it brings in information from many models. It can include specialized models such as the WRF RTDA. It can include global models, both from the US as well as other countries. But the key is leverages observations in the field, and it trains over a period of time. It does a two-step process where it bias corrects each of the models individually, then it optimizes weights into an integrator. For wind energy, we use actually the data from the nacelle right on top of the wind turbine. Now you say that may not be perfect for the inflow, but the advantage of using that, it is the wind measurement that is most highly correlated to power output. So for wind energy applications, we're finding that it's very successful to use the nacelle winds. Okay, but of course, again, the end user wants power, so there has to be a power conversion. Again, we use a machine learning method and then come out with a wind power forecast. Now, the result is each of these colored lines indicates error according to the lead time, an RMSE, for all of the input models after they've been bias corrected. And we see that the die-cast output, the solid black line, by design will always have a lower RMSE on average. And for wind speeds, we find that we typically see a 10 to 15% decrease in error over the best input model. Now, for the end user, this makes a real cost savings because they're able to operate their system more efficiently. Xcel Energy did an analysis of changes in their day based on a day ahead forecast and unit allocations they were able to use based on that on NCAR's wind forecast system. When they were starting the project, they were using general numerical model output. They had a 17% mean absolute error there. And by the time the system was delivered in 2014, the error was down to 10%. Improvements later brought that into single digits. This is a 40% increase that they find saves their ratepayers about $10 million a year. So over a 6-year period, it saved them $60 million. Now, in addition, because they were able to optimize the use of wind energy, they also found that they saved over 267,000 tons of CO2. So that is real emission savings by forecasting. NCAR was honored to get the CoLab's Governor's Award for Sustainability, a team that included some folks from University of Colorado as well as NREL, and we included our Xcel partners also as part of that, and we were able to receive this award on a very cold November evening. So we were successful in building a wind power forecasting system, and many of these methods have been picked up by the private sector now. So in around 2012, we wrote a proposal to DOE Sunshot to improve solar power forecasting as well. And for that project, it was a team approach. We used a value chain approach where we looked at weather on the left side of this chain, where weather happens, and for solar forecasting, it's basically clouds and aerosols. And the goal at the end is to provide economic and social values. So we do that through providing monitoring in situ as well as remote sensing observations, lots of modeling, both in terms of physical modeling as well as machine learning modeling, forecasting on both day ahead and very short range timescales to produce point and area forecasts that are then disseminated and communicated via power conversion, quantifying the uncertainty. The end user perceives that, so they can project their power production. Then they compare it to the actual power production to do load balancing. And that allows them to make real-time decisions, both day ahead and for real-time operation on unit commitments, as well as how to operate their reserves. That can result in real changes in production costs and the reserve operations. End user, in this case utilities, independent system operators. Basic research community is sometimes pretty disconnected from where the end user is. So to bridge that gap, we have to include applied research, in this case a funding organization, DOE Sunshot, monitoring as in an operational sense, computing, running numerical weather predictions operationally, and then translating it to reach that end user. And this certainly was a public-private academic partnerships where we brought in the end users and also had lots of research organizations, national labs, universities. We had the translators in terms of various private sector forecast providers as well. So again, the uses here were both day-ahead unit allocation as well as grid integration in real time, and we produced what we called sun forecast system that was a fully operational system. Here is a wiring diagram where a day-ahead system operates using numerical weather prediction models, integrates machine learning via diecast, a nowcast system where we have satellite observations, total sky imager information, integrating all of this with machine learning, merging the two, converting to power, applying analog methods to make that a probabilistic prediction. And we published the results, and we find that the forecasting community, especially because they were involved in the project itself, have been picking up many of the techniques. Now, since that time, we've been working with some other countries, in this case, the Kuwait Institute for Scientific Research, to produce a fully operational renewable energy prediction system we call CREPS. Like our philosophy for building these forecasting systems, we blend the physical models with the artificial intelligence machine learning models so that we end up producing a probabilistic forecast that they can view and use to operate their systems more efficiently. Now, let's change directions and scales a little bit and talk a bit about the need for better coupled modeling. And this is going to lead into a project with the Wind Energy Technology Office of EERE and DOE. And as motivation, these plots show two animations done by Matt Churchfield of NREL, where we have the wake from one turbine impacting wakes on the downstream turbines on the left. And the plot showing power output in that case is black cumulative power on the bottom middle. Versus if we're able to control and point the front row turbines in ways to minimize the impact of the wake effects on the downstream turbines. And we found in this particular simulation about a 14% improvement by being able to control the wakes. Now on the right is an animation from Lawrence Livermore National Lab showing frontal passage through a wind farm where you have rapid changes in wind speed and direction. Now, to understand that requires coupling the mesoscale models, that inflow from the larger scales, the energy spectrum we saw, with these fine scale models to look at details of what happens in the wind plant itself. Now, over the last 6 years, a group of laboratories have been working together, specifically in addition to NCAR, Pacific Northwest National Lab, National Renewable Energy Lab, Lawrence Livermore National Lab, and for a while we also had Argonne and Sandia National Labs involved in a long-term project looking at mesoscale to microscale coupling, looking at developing real usable techniques that can help everything from wind farm siting, control, micrositing, and maybe eventually impacting forecasting. So we grounded the project in data, looking at flat terrain, complex terrain, offshore wind energy. By doing case studies, we were able to develop methods and determine what methods worked best. We begin with a mesoscale model. We want to couple to the microscale, but to do that, we have to bridge the so-called terra incognita or gray zone of about 100 meters through on the order of 1,000 meters or so. Now, because the mesoscale doesn't resolve turbulence at the microscale, we have to develop methods to initialize turbulence. We have to have some sort of consistent surface and boundary conditions across these models. We ground this in verification and validation with uncertainty quantification, and the goal is a more realistic forcing of turbulence resolving simulations through this thing. I've had the privilege of leading this project over the last 6 years. It's coming to a close now, but we've made some rather nice progress. Now, first, I did mention that terra incognita. Carolina Draxel at NREL did a nice job demonstrating what can happen, how those spurious rolls that are really numerical artifacts show up. At 3 kilometer simulation, we see a nice wind field. When we go down to 1 kilometer, and for this convective case, we start seeing the spurious rolls when we're right in the middle of the terra incognita, 333 meters. The spurious rolls are certainly there, and we confirmed those were not real. So how do we define this a little bit better? This is where Raj Ray and Larry Berg at PNNL developed some very nicely crafted numerical experiments to study convective conditions, where they looked at grid spacing on the order of 3.2 kilometers, 2.4, and 1.6 for cases that had boundary layer depth of 1.6, 2.4, and 3.2. And the big finding was that one could define the terra incognita as the height of the boundary layer. Now, when you think of it, that makes sense because we confine those big rolls within the boundary layer, but it was a new result in the literature. I gave the citation here on the bottom. Also, that we find that we have more energy at the microscale when it's coupled to a mesoscale nest. So that was a first scientific question that we felt we were able to contribute to solutions. What are the best coupling strategies? That was, of course, one of the big questions. Mesoscale models can capture the full variability of the large-scale flow. We have physics parameterizations, things like radiation schemes, surface layer schemes, boundary layer processes, cloud physics parameterizations, etc. But microscale models are necessary to capture the details of flow around objects, and they are very useful for those control simulations like I showed a moment ago, looking at loads on turbines, doing very details of the siting. So to get the microscale models having that mesoscale impact, we have to be able to couple them so the microscale model dynamically follows the mesoscale flow. And the approaches one can use is, first of all, direct nesting of an LES in the mesoscale model, such as the Weather Research and Forecasting or WRF model enables. Or we often use standalone models. And in that case, we have to find a way to force. And one way of forcing is to basically assimilate tendencies from the dynamics. The coupling strategy portion was led by Matt Churchfield at NREL. He liked to divide this into different ways of looking at it. You know, when you couple the communication directionality, one-way versus two-way, the strategy, online nesting versus offline through some sort of file input, what information is transferred, either the direct quantities, mean quantities, fluxes, etc., or indirect quantities, a budget, such as the tendency assimilations. The information location, whether we just force at the surface and the inflow versus internally through a volume approach. And we've been doing some comparisons that we're in the midst of publishing now. Now, I love this animation by Matt, where he showed what one can do with a fully coupled model. This is, this is the wind speed. You can see the local time here on the bottom right. Early in the day, we had the fine scale turbulence. As the sun is impacting me more, we get the convective rolls, then the convective cells. And as we are at midday in local time, and then as we progress to later afternoon, the sun angle is going down, the warming is less, we go back toward the smaller scale turbulence. Again, this is enabled because the simulation was coupled to the mesoscale to get this beautiful diurnal cycle. Another question, what are the best ways to generate turbulence at the microscale? And this is a collaborative effort of all the labs led by Jeff develop. There's a long fetch, and it's very expensive to waste a lot of grid on just spinning up lens. Now, there's various ways that you can do that. We've been experimenting with stochastic temperature perturbations as well as momentum perturbations that work quite well. We've also been looking at methods that are more parameterized, like Mann and Veer's method. The team is investigated is most useful for what particular situations. Another scientific question, how do we represent the complex surface layers? And in work led by Raj Ray and Larry Berg at PNNL, looking at simulations in the very complex terrain of the Pacific Northwest, doing case studies, showing that one can simulate wakes in the lee of Mount Hood, as well as very fine scale turbulence, for these situations, by using this nested coupling, and we're able to get a fairly good match of the energy spectrum over a pretty large area, and the LES does fairly well until we meet model resolution. Now, at NCAR, we've been looking at model improvements, and specifically one application using machine learning for surface layer parameterization. Now, we want to get the flux transfer between the surface and the atmosphere, and traditionally models have used Mononubicoff similarity theory. But because it's a similarity theory, we need to fit coefficients from measurements, and a lot of that was done from prairie grass measurements back, in the 1960s, 70s, and that's flat terrain, grassland, so it's very limited, but most models use this. So it's really low-hanging fruit to train a machine learning model. It is hard to find sufficient data. Some good data we did use for this was the KNMI mast in Cabot, Netherlands, as well as a tower in Schofield, Idaho. We were able to fit both a random forest and a neural network. We find both of them have better agreement with observations than the Mononubicoff theory. And we find it's true even when we apply the model trained at the Netherlands to the Schofield site and vice versa. We've been implementing that in WRF. We're finding very promising results, and we're also looking at implementing it for offshore. The data for the offshore was derived from the Pheno Tower off the coast of Europe. Again, you see that both friction velocity and temperature. We were able to get much lower MAEs with the machine learning models than we were with Mon and Ubicoff theory. Another advantage of the machine learning is that for the random forest, we're able to look at the importance of the various variables, finding the potential temperature and mixing ratio are important variables, but so is the water surface temperature, wave height, and then that's even more important than the 40-meter wind speed and wind speed gradient in Mon and Ubicoff. Now, another thing NCAR has been doing is developing a three-dimensional PBL scheme for WRF. This has been done by Branko Kosovic, Pedro Jimenez, Tim Giuliano. I love this animation of 30-meter flow in the Mount Hood, where we have inflow from the left. We see this beautiful meandering wake developing in the lee of the gravity waves forming along the ridge along the mountain. We see gravity waves being transported downward as well as stationary, cold pools developing. This really enables great simulations to have that fully 3D system. But of course, it takes a long time to run a simulation like that. So it took several weeks using 8640 cores. So more recently, we've been looking at, can we use machine learning and specifically deep learning to downscale? And Sue Detling has been leading a team to apply an enhanced super resolution generative adversarial networks to do a 32 times downscale from 960-meter WRF simulation to the 30-meter super resolution. And indeed, we find that we can recover the fine scale detail using this machine learning method. And the advantage is the application takes order of seconds. Now, the team has been developing Jupyter Notebook tools, such as looking at how long it takes the turbulence to develop from the inflow, can plot energy spectra for various methods, distances down, do very good comparisons, plot PDFs, and we're releasing these. And in fact, we're building a model repository of all the in this project, including the Jupyter notebooks for assessment. We're preparing and documenting case study workflows so they can be replicated and adapted to users' need. So we're in the midst of making this public, reporting our lessons learned, and in September, put this on your calendar, September 14 and 15, we're hosting a virtual workshop for wind energy professionals interested in doing their own applications of these techniques. And if you have questions, please either contact myself or Amy DeCastro through our UCAR emails. Okay, finally, I'd like to end with talking about interannual variability and looking more at some climate scales. And in particular, as motivation, I wanted to look at the difference in wind energy. This is January average wind speed, a difference between an El Nino year, 1998, versus the following year, 1999, that was a La Nina year. Now, if you look carefully, if you're in Northern California, the difference there was a positive 6 meters per second in 1998 versus in, we saw a negative more than 6 meters per second in Southern California. Now think about how that translates if you're on the steep part of the power curve. and you have that cubic relationship on power output, that makes a huge difference. So we need to understand this interannual variability and also what is going to happen as we see our climate changing. Now, we had a project with NREL a few years back where we were looking at coming up with means and annual variability statistics for both current climate and future climate over a 20-year period. For that project, we leveraged NCAR's Climate Four-Dimensional Data Assimilation Database for current climate, where we had high-resolution data hourly, and we were able to draw these mean maps of wind speed across the United States, see the areas where there's an excellent resource and a few other areas where the resource is not quite as good. Now, we looked at the standard deviation, in this case, an interannual variability, and we see that the variability, as one would expect, kind of matches the same patterns as the mean, but it can be rather large in the regions where we're deploying the most renewable energy. So it's important to understand that. Did similar analysis for global horizontal irradiance. As one expects, the southern areas of the US have the largest resource, but also the largest variability in that resource. Now, the purpose of this was to apply this in NREL's READS models, where they can look at optimizing deployment of renewable energy for both current and future climate. And it works on having very small regions, 356 across the US, and it also requires information by time of day. So we sliced the data into morning, afternoon, evening, night segments, and also by season. So doing this for our 20-year climate database. Again, we were able to produce means and variability. We further broke that down for analysis using organizing maps, which is based on neural networks. We see plausible patterns of, these are wind maps, wind speed anomalies over the United States that we're then able to use to analyze and project onto the climate models. So beginning with current climate in climate models, we looked at several combinations of global climate model coupled to a regional climate model, looked at variations and which ones represented the SOMs best, chose the CRCM, CCSM combination, and used that to project for future wind and solar output. Now, to project our SOMs, we did this in terms of SOMs. We applied SOM-specific climate adjustment factors for each season. And you can see different patterns for this particular SOM. We use the output then to form a proxy database of future climate and look at projected changes between a climate that is centered on 1995 versus a 20-year climate centered on 2060. And again, we sliced and diced according to very different regions, seasons, and time of day. And we find that for wind, we do see some seasonal and regional patterns where there's a projected decrease over portions of the US in the winter, but increases in the fall and summer in those regions. Decreases on the eastern US for spring and fall, but increases in the northeast US in the winter. So these differences can make a difference in how we deploy wind energy. just a picture. I'm not going to go into detail. We selected, which versions of climate and regional climate models that we chose, calculating frequencies, projecting this future proxy climate by leveraging the calculations of the self-organizing maps. That allowed us to produce these maps. We found that the frequency of occurrence in patterns is about plus or minus 10% on average, though at times we could see it exceeded plus or minus 20%. Regional changes are again within about this plus or minus 10%. We saw a strong seasonal dependence, but not a strong diurnal dependence. So in summary, by using meteorology knowledge, we're working toward a successful energy transition from the old paradigm of having fossil fuel usage that is polluting our atmosphere, raising the global temperatures, to a new one where we see a better energy future, where we have clean, renewable resources. Right now, we're in the midst of the handoff from the old paradigm to the new paradigm. So in summary, we have this collaboration between the energy and meteorology community. We need that collaboration so we can better optimize use of our renewable energy. It's equalizing the potential access to energy as there are no boundaries in the atmosphere. It's globalizing the energy resources. And we're finding that the weather and climate information that is being provided, it's really required to integrate these variable renewable resources well. And the outcome that we see in the future is a clean, affordable, accessible energy future for a better world. So, and hopefully equalizing societies as well. Thank you.
Thank you very much, Suella. This has been a great presentation indeed, with so many messages, very interesting. Thank you very much. So, for people who are currently online, please feel free to type your questions, if any, in the Q&A. I have a couple of questions already, Suellen, and we have, I think, around 7 minutes. So, what you have shown is the modeling of atmospheric loads, and I would like to ask you, in let's say, in parallel with climate change, do we see the loads changing? Can we quantify the impact that climate change has into the modeling of loads?
On the loads as well?
Yes.
Yes, and that's a very important question. We did some load prediction for a while for Excel Energy and found that leveraging existing information is able to better predict loads. But you do pose a good question. As we have a warming climate, that's going to impact loads. In addition, we saw the pattern of the countries who use the most energy are also the most developed. So as we begin to equalize, we may see energy usage going up in the developing countries as well. I think that we could see substantial load increases. And when you look at, documents like the REN 22 does project where loads will be in the future. And, we do see growing loads, which makes it even more important to deploy the clean renewable energy if we're going to have a livable world in the future. So good point. Thank you.
Mm-hmm. Thank you. And another question is that for many of us, the loads are the inputs. I mean, many of the fellow scientists, we are working towards developing the technology further. So I would like to ask you maybe a naive question on how accurate do you think are the models that we are already using? how accurate is the representation of the real thing?
Okay, so it appears that I temporarily lost
Can you hear me okay now?
internet, but
Can you hear me?
yes, I can hear you.
So the question was that many of us are working on the development of the technology, and the loads is used as an input. And I see that there is significant research already taking place in order to improve the models that we have for loads. So how accurate are the models that we are currently using?
Mhm.
What's the uncertainty like, the modeling uncertainty that we're facing?
Yeah, and you're right. Using the best information. Load models have always used temperature as well as usage information, but now I think we're finding that using more variables, applying machine learning, can do better predictions of load. Looking into the future, applying information from climate models can then help project loads in more details and load patterns, that might happen under future climate scenarios. And of course, there's large uncertainty in the climate scenarios. And due to the expense to run the climate models, we often focus on a few scenarios, but there's a wide range. The hope is that we'll deploy more renewable energy faster and avoids the consequences of some of the more problematic scenarios and pathways.
And a similar question which came from the audience is that knowing that most consultants in the wind power community are still using very basic engineering models for wind resource and wakes, how do you see the gap being closed between those different players?
Mhm. And that's really a good question too. Is there's been teams. Our mesoscale microscale team is certainly not the only one working on these issues. There's people, researchers around the world. There's other DOE teams developing better wake models. We can do these large eddy simulations of wakes now, and through using some of these deep learning techniques, perhaps come up with very rapid methods to do predictions on wakes. But those same teams that are doing the LES are also coming up with improved lower order models and parameterization models. So again, a lot of the researchers are making these public so that we can use these, and really the end user can use them themselves, or private sector that is consulting for the end user. The goal of the researchers is to make this broadly available.
Thank you. And we have two more questions, and with these questions we can finish. So the first one is, you mentioned that microscale simulations predicted more energy when nested in the mesoscale. And can you explain a bit more on so were microscale simulations consistently under predicting energy outputs? Are there some reasons associated with this?
Okay, now if I get the question, if you do nothing to a microscale simulation that is forced by a mesoscale, it takes a long time if it develops sufficient turbulence. And that's what we found in our teamwork. You need to do something. And if you nest it, the nested model will eventually develop turbulence, but it does take a long fetch, and there's the correlated time that it takes to develop turbulence. In complex terrain, the turbulence develops much more quickly, but adding these stochastic perturbations really saves that fetch. And we're finding that, if there is some reason you can't add that, then you're able to use these parameterized models like the Mann and Veers models and still get turbulence develop. We're coming up, and again, we're releasing the code that does develop these stochastic perturbations for both temperature and momentum.
Many thanks. And the very last question is from Johan Myers, and I think that this can help us summarize the story. So I was wondering, Johan asks, how good predictions can become given weather is a chaotic system, and how much improvement do we still have?
Okay, would you repeat the last part of the question?
Sure. How room for improvement do we still have into modeling?
Oh, yes. Of course, research can go on forever. We think we've made some big steps in our project in the last 6 years. Again, we are in contact with our European and other collaborators. We're not the only ones making progress. We certainly, we've just begun to look at the offshore environment. New projects are going to begin in the offshore environment. In the US, one of the big areas for coupled modeling is extreme events, especially because we're talking about deploying wind energy in regions that experience hurricanes on a regular basis. We need to understand that better. Also the extremes in the opposite direction. What about when you have large-scale high-pressure systems where you may not have wind for over a large region for a period of time? There's a lot of things that we need to model better. What about in cold regions where we have wind turbine icing? What about erosion on the leading edge due to precipitation and hail? There's lots of good researchers around the world working on these problems, and there's a lot of good scientific questions out there, and I look forward to working with the community on these issues going forward. It certainly is a lot of fun, and we're doing good for the world by enabling the renewable energy that will equalize social equity. At the same time, it's providing a cleaner future. For that, Johan.
Fantastic. So, and on that note, I think we can close the session. So, on behalf of the Academy, I would like to thank you for this presentation and for your sustained contributions in our industry. And I would like to congratulate you once more for this well-deserved award. So, closing, I would also like to acknowledge the great support from Jana Brewers and Peter Pauletta, as without their help, we wouldn't be able to hold this session today. And finally, I would like to mention that the Academy will be launching a series of lectures like this in the next few months. So if you find this session interesting, please stay tuned and you will receive more of our news. So thank you very much all for attending this session.